Okay, so hi everyone. So welcome to this second session, live session with Eric. And so Eric, before you start, I will just present my slides. If you can, okay, so I will just share the screen. So can you see my screen?
Yes.
Yeah. So first I will present a brief biography of Eric S. Reiter. Then I will talk about my research work on electromagnetism with moving objects and numerical simulation of the Compton scattering. And I will talk a little about the long tradition of wave model for Compton scattering. And then I present Eric's beam splitter coincidence experiments. Eric will give more details about these experiments and also the double slit experiment. So there is an interpretation based on the threshold. And then I will give the floor to Eric. So this here. So Eric Reiter is a lifelong independent researcher and inventor with a deep passion for exploring the foundations of physics. He studied physics at California State University and has published papers in Progress in Physics, Physics Essays, and the 2015 SPIE conference, What Are Photons? From 1980 to 1995, Eric led the company Computer Continuum, which developed laboratory and automation add-ons for personal computers. Earlier in the 1970s, San Francisco's Exploratorium Science Museum featured two of his innovative exhibits, the Sun Hub and the Solar Living Sphere. His website, www.thresholdmodel.com, presents the full scope of his research and inventions. So to explain why I was interested by Eric's works, I will present my research work on electromagnetism with the object in motion. So this is recently we worked on this subject. The way we analyze this problem, we use only Maxwell's equation. We don't use Lorentz transformation, and we divide the problem into time frame, and within one time frame, we use Maxwell's equation without any transformation. We don't transform electric field and magnetic field, and we don't transform the space variables and the time variable. So with this method, we can analyze the problem that was not possible to analyze using Lorentz transformation. And we can see, for example, we detect here the radar cardiogram. The blue one is experiments from the literature, and this is here our simulation by using finite difference time domain method. And we did that also for respiration. So the red one here is measurement, and this is our simulation. This is unique simulation that we have performed. And we also do that for other kind of electromagnetic problems in the presence of object in motion. And based on that, I wanted to extend this model for other problems, for example, for the Compton scattering. Our first paper on this subject, in that paper, we use a moving source. We have a source which has a certain wavelength, which is actually the Broglie wavelength. And based on the classical Doppler effect, which is, you see here, this is a Doppler effect for a moving source. We replicate the Compton wavelength wavelength shift if the velocity of the source satisfies this formula. And then later we found that actually we can replicate the same if the particle, it is a moving particle. I want to say here this is this particle. What's important here is a boundary condition. It could be something more complex, but it will not change the the formula for the Doppler effect. For here, for simplicity, we represented it as a particle, so just a sphere, but if it is more complex, it will have the same type of formula. So in the moving scattering particle, the Doppler effect has, you see the denominator here is a Doppler effect for moving observer, and the numerator is a Doppler effect for moving source. Let me put this here. So this is a Doppler effect for moving scattering particle. And we can also replicate the same Compton shift using this model. And after discussion with Eric, I'm working on another model where the particle is not moving in the same direction of the direction of elimination of the X-ray. So that will change the formula for the Doppler effect.
Good.
And then here I would just want to say that there is a long tradition of the wave model for Compton scattering. And this started with Raman in 1928. And when you read his paper, actually, you can say this is within the framework or within the idea of the moving source model. And other people also analyze the same, use the same similar idea. And there is Kidd and others who use a moving scattering particle model. So the Doppler effect that I showed before. So novelty in our work was to propose a numerical method based on Maxwell's equation to replicate this phenomenon. And this is also this from a Compton book, which Eric suggested me, which we can say it is within the idea of the moving source model, but with more details about how the source is behaving. So in that model, electrons themselves, they are waves. And we can see here the Bray idea about the Bray waves and the source idea too, moving source. And here just I will go fast to say that in 1927, there was the Solvay conference, which the title was Electron and Photons. And in this paper, they reproduced the proceeding of that conference. And the people who were present, there were Bohr, Einstein, Schrödinger, Heisenberg, Dirac, de Broglie, Compton, Bragg, and Lorentz. And I just asked ChatGPT to see where they talk about the wave-based model concerning Compton shift. And they say that Compton talk about that. Don't go to all what they say. Also, Schrödinger proposed some ideas, but Lorentz said that we have to look about the boundary and interaction condition. And he also talked about Maxwell's. Lorentz talked about how we can use Maxwell for this problem. And there is also some work done by Bragg, but this is only wave model of scattering of X-ray. And they talk also a little about the BKS model. And I think I will just go to the next one. So today we will talk about the beam splitter coincidence experiments. So I will go fast on this slide because Eric will say more about that. And we will see if we have time today or for our next live session, we will talk about the double slit experiment and the interpretation that Eric has that I found very interesting. So for Eric, you can correct me if I'm wrong. Either it is light or electrons or matter waves, they all behave like this, like waves. They spread like waves, they diffract like waves. But when the energy is very low, we will not see that. We will not see all these waves propagating like this. But at the detector, if the detector reach a certain threshold, we will see a click. The detector will looks like there is a particle, but it's actually it was not a particle. It was the waves from the beginning. So this is usually the representation of the double slit experiment for electrons. So in Eric's model, we will not have this electron here, but we will more have something like waves. But at the detector, we can detect one at a time, or I mean, something looks like particle detection. I just put this water wheel analogy. Maybe we can use this kind of analogy. The water itself is almost continuous, but
No.
when it will go to the wheel will turn
No.
with a discrete way. So like there is this quanta of energy to make the wheel turn. But I don't know if this is a good analogy or not, but I want to have an analogy. So now I will leave you the floor to Eric, and thank you for
All right. Thank you.
so I'll stop to share. Okay, so we can see your screen.
I
Yeah, you
see
can.
you, but I don't see my screen.
I see your screen,
You
and
do?
I think if I go to just to check on YouTube, if I see. Okay, we only see me.
Right.
So why is that?
It's a
You
Zoom
have to,
thing.
you have to share, or I stop my video.
It
If I stop.
it's a Zoom uh, where you choose in Zoom what that the
Okay, so I don't share my
attendee.
video. Now we see you.
I can see what Zoom is doing, and I just see a picture of you.
Okay, now I see your presentation.
You
I,
do?
yeah,
Really?
yeah. Now I see. Yes.
Okay, but I don't. All right, I'm just going to believe you. So let me correct something that happened before. It's not that it's a rain of particles or that it's a weak beam that lets you see whether it's a wave or a particle. It's about how you do the beam split experiment that shows the distinction between the wave and the particle model. And so the history of this experiment is outlined in this uh, quote of Einstein's work. It's Bohr paraphrasing Einstein's model of the photon, which is about that whatever a photon is, that it's quantized, it'll go one way or the other at a beam splitter. But if you were to reconverge the beam, you see over time an interference pattern. So my work is about this first part of the photon model to show that the way they see that it goes one way or the other was just never done properly to see the alternative, which in the history of physics, it was called the loading theory. I perfected the loading theory and I call it the threshold model. And I'm showing that what goes across space, it may be initially uh, like a quantum Planck constant times frequency, but then thereafter it spreads classically, and that it can go splitting to both detectors, and that the threshold is that there's some energy in the detector ahead of time that you get to see if you do the beam split experiment in a way to unveil the illusion of quantization. So the threshold model includes the idea of what looks like a quantum, but there's a sub threshold that we're able to see in this experiment because the way what happens is that I'm going to start with one and end up with two. And the idea is how do you get two when you start with one? The answer is that there's something there ahead of time, that it's a loading theory. And people did not understand that theory, and they never tested it properly to see the distinction between a loading theory and a threshold and quantum mechanics. But that's what I do. So that's some of the history. And now I'm going to go to change the scene to my Canon camera. I'm going to switch over and look at the actual apparatus and let my camera person take over. And so what let me just go on the pen board for my let me just finish a few ideas about that, what I was saying on the pen board. There are two main advantages that I have over the way other people have done that same beam split experiment. And that's that I have pulse height resolution. So if you do a spectrum of visible light, you'll have pulse height, but it's a wide distribution for monochromatic light, and that's what they do. So they're not saying anything about the pulse heights, where they set their pulse height level discriminators. They're not saying anything about that. To them, all of these pulses that come out with different heights, they're all thought of as photons. And that's a big mistake because you do not get to do what I call an energy budget, which is important to do this 2-for-1 uh, measure to make my case that quantum mechanics fails. So that's what visible light does. But a spectrum of gamma rays, it'll have an X-ray, then there'll be some Compton shifting, and there's the photo peak, and then there's some pile up. So there's a whole spectrum of pulse heights. Bigger pulses go this way, the number here. So you get to pick out energy, pulse height energy in electron volts. Everyone will say this is a photon energy, but we're doing a test of the photon, and we're showing that it's really just energy of detection. So the energy of detection is proportional to the height, is proportional to the electron volts, and it's also proportional to the electromagnetic frequency on the horizontal of these pulse height spectrums. And we'll get to the pulse height spectrum. So I have that major advantage in doing it with gamma rays. And nobody has done the beam split coincidence experiment with gamma rays or alpha rays, and I do both. So the other main advantage that I have is that we have an assurance that the emission is one at a time by doing what's called the true coincidence test. And the nuclear physicists use it, and everybody agrees on it. That if you have two detectors and you have a radioisotope in the middle, and if it emits two, it'll go to the system where you see on the oscilloscope a time histogram where the time difference between them will, if it emits two at a time, it'll make a peak in that histogram of plus nanoseconds and minus nanoseconds. We're going to look at this peak quite a bit. But if it emits one at a time, it'll look like noise, a band of noise here. Now, other people, when they've done this experiment with visible light and they do the beam split, they use that same histogram and they just see that band of noise. And that's what quantum mechanics would predict. The band of noise in the delta t, the time difference histogram, the time between clicks in the detectors. And so if it goes, we're going to look at this in a minute, but I want to explain this histogram. That's what it's all about. If it goes click, click, it'll make a point on the left of the histogram. If it goes click, click, it'll go on the right. And so all these points build up. If it goes together, it makes a peak in the histogram. For it to go together in time, it's about doing something better than random accidental chance. There's a mechanism, there's a reason for it to go making a peak. And they know about that. We do tests. And so we know that if it goes together in time, it goes to both detectors more than accidental chance. And the previous papers that I've shown in my lectures they do the same thing. They admit that if you get a peak in this histogram, quantum mechanics needs to be adjusted pretty radically. So now we can go, let's take a look at the real thing. Let's look over here where the experiment is. And you're not going to be able to see much inside. Later, if you'd like, I'll bring the camera over to see what's inside. But what's inside are a I have the setup, I call it tandem geometry, where there's a thin detector in front of a thick detector. Uh, Now, I've done it where it looks like a beam splitter, but this one is the one that I'm uh, recommending that other people start with to do the experiment. So the thin detector, the detector is a scintillator crystal of sodium iodide that makes a small flash of light. If you stick your eye on it, you won't even see it, but the photomultiplier tube can pick it up. The brightness of the flash gets converted to the size of the pulse that gets read on the oscilloscope. And so this is a Hamamatsu R647, this small photomultiplier tube. The scintillator can be purchased from Saint Gobain, and I've also imported these from Ukraine that work quite well. But you have to see the inside of them that they're clear to make sure that they're good from the picture, because there are many bad scintillators. They have to be perfectly good scintillators. There's a resistor divider inside, and it's also possible to just purchase this together, or the socket with the divider on it, which saves a lot of work. And then it's good to have an amplifier. It's optional to have a preamplifier on it. The polarity is important because the metal here at the end of the photomultiplier, it assumes ground potential at the front, which is the cathode. So the way it works is that the power supply is a positive for driving the circuit. And the circuit diagram for the resistor divider is at Hamamatsu's website to show how to put that, to show the values of the resistors. The other detector, now it does not have to be as large as this, but this makes the best results for several different kinds of experiments. I've done like 1.5 diameter here. This is about 3 inches. This is also a sodium iodide imported from Ukraine. They'll say, instead of NaI for sodium iodide, they have a J here, so don't be confused about that, for sodium iodide. Parentheses TL, thallium doped sodium iodide scintillator. Now, the detector is important because there are detectors that have better pulse height resolution, but give a more difficult to see unquantum effect. I call it the unquantum effect when we get a peak in that histogram and it defies quantum mechanics. So there's, I'm going to go to show how to put this detector together with the parts. And so it's a scintillator, and so you could see inside that it's perfectly clear. That's really important. You could see the back of it, no fogs or anything. And so there's special grease that you couple it together to a photomultiplier tube. And what I do is I glue around the edges to stick them together to make them hold together. And then you have to wrap everything so it's perfectly light tight with black tape. And so you end up so that it's possible to make the detectors, the scintillators. It's a lot less expensive. Of course, you can just buy it all together, but it's risky business because these detectors, I found that they can go bad over like 20 years. They start to fog up. So it's risky unless you buy them new or guaranteed. to have it all put together for you. So there are different ways to buy the detectors. There's another detector that I had a lot of good progress with, where I had this made special. It's a 4 millimeter thick detector. There's a window at the end that a photomultiplier gets coupled onto. And the gamma rays go through and then to the next detector to see if it can go to both detectors overlapping in time. And so I have good videos to show this one working. But it broke. I don't have it anymore. It doesn't work anymore. So that's about the detectors. There are other ways to make the detectors. I've done scores of ways to put together the detectors in different arrangements. It's all on my website. And let me quickly show the radioisotope. The radioisotope that you purchase, it's a coin shape, and I recommend that you buy 50 microcuries of cobalt 57 and in this form factor. And I mount it on a stem of wire to handle it. It's not really dangerous, but you don't want to wear it, be close to it. It's emitting 122 keV gamma rays. This is not that same radioisotope. This is a different one, but it looks like this. So, and so it gets placed in between slabs of lead. Now, you have to make the collimator to to uh, to make it go through both um, detectors. When they sell you the radioisotope, they'll package it in this lead container like so. And it's possible to flatten this out and use it to make the collimator. So you put I'm going to draw the side view. And so here's the radioisotope, and then there's a slab of lead and a slab of lead. And then you do something on the top and bottom to keep it from going that way. And so there's the small detector and the big detector. And the rays, you have to set it up so that the rays go through the first detector to get to the second one. Whatever the second bigger detector gets has to be what went through the first detector. And then you see, well, if it goes click, usually it goes to one at a time. Click, click. But if it goes two, it's not a photon. And that's what the experiment is about. So now we're ready to go to the real thing. So let's frame it here. And so we're in front of the LaCroix oscilloscope. And now there may be other ways to do this experiment. I do not recommend it. What most of the other modern equipment, what they do is they make you use the mouse for all the controls. And I find it very clumsy. And I find the user interface of the LaCroix coupled to the NIM bins. So the NIM modules, nuclear instrumentation modules, is something that many laboratories will have already for their nuclear physics experiments. They may not have enough to do it. They'll have it for like one channel to see gamma ray spectroscopy. And so I have the two channels. I'm going to take away a few things here so you could see more of what's going on. So you have to start out understanding gamma ray spectroscopy. Uh, so there's an amplifier and a single channel analyzer, which is a filter. The filter is there's a lower level and an upper level, and you have to set where you want that. And so I'm not counting the smaller pulses. This is a histogram coming through this from the small detector that's being also triggered and filtered. So on the LaCroix, you get to see everything. You get to see the pulses that are happening. You get to see the pulse heights, spectrums on both channels, and you get to see the time histogram. And there's these timing. You get to see everything. It's really a great system. But you have to set up the LaCroix. You just press some buttons to make it happen. Before I forget, I want to say what's important about getting the LaCroix. It has to have the software that does the histograms, and they don't always have that. So if you were to try to find this, you go to scope status, and you may ask the seller of it because they're used and the seller won't even know how to do this. So you say, go to scope status, you go to system, and then here you see WAVA. That is what's required to do the histograms, to see everything here. You can have it installed afterwards with some large fee from the manufacturer, and I've done that. So, and it's even worth it to do that. They charged me about $1,000 to enable this software on one of my scopes. So you get the histogram software, the right kind of oscilloscope, 4 channels, wave runner. It's great. So back to the NIM modules. What this is about is that you really want the amplifier and the single channel analyzer to have the property to eliminate what's called walk, where let me go back to the pen board to explain what walk is. So there'd be different pulse heights, and so if there's a small pulse height, it does the time pickoff. If it's the wrong kind of amplifier, the time pickoff will be a function of the size of the height, the amplitude of the pulse. So there'll be a time pickoff here on the wrong amplifier. If it's the right kind of amplifier that has a walk specification and it's used with the SCA, they go together. So anyway, it'll pick off at a different time maybe. And so they give specifications to get within a few hundred nanoseconds to minimize this error that happens with different pulse heights. And we're reading in, we can read in on many experiments a range of pulse heights. And so you want that to be a minimized error to do these experiments. So that's about how you buy these NIM modules to make sure you're getting the right thing. So there are a few numbers that I can rattle off as to which ones to get. There's the 551 is typically the kind of timing single channel analyzer. Now, at least one of these SCAs have to have an ability to adjust a delay to shift the timing pulse so you get to read the time difference between them over a range of times. So this delay is important. And so anyway, that's Ortec 551. The other, there are a few possibilities to use. This one is an amplifier and a timing SCA, and it has a switch on the side that lets you have a time shift on it, because this does not have the knob for the delay, but the button on the side will work. So this model is kind of nice. It has the gains and the upper and lower level where you set the which pulse heights you want to use. And I don't know if I think I didn't explain that about the uppers and lower levels. So back here. So you get to set on these pulses If there's small pulses, you want to eliminate them. They're like noise. They're the X-ray. You do not read the X-ray. In the pulse height spectrum, there's the X-ray, and then there's the photo peak, the gamma ray. And then there's some other, so this is height, pulse height, and this is time on these two graphs. So you get to set the lower level where you eliminate the X-ray, and the lower level on this graph would be here. You get to set the upper level of these pulses, and that could be wherever you want up here. You can, there's some interesting phenomena that happen on these bigger pulses. The bigger pulses are when two, let me draw a picture of a scintillator. Here's a scintillator, and there'll be a gamma ray that comes in, and it'll go flash, and then another flash can happen within, and there could even be 3 or 4. And I've seen that. I've shown it, that there could be more, and it could happen more often than accidental chance. And that's what it's about. And it's an easy calculation to look at the spectrum and do a calculation to see if 2 of them overlap in time from one at a time emission. So that's what's really great. I'm using a source that's emitted one at a time for sure. 1 gamma ray per spontaneous decay of the atom. In this case, it's cobalt-57, emitting a gamma ray. And then it makes 2 flashes or more, flashes of scintillator light that's characteristic of the 122 keV. And then you get a big pulse. So you get to see, even with one detector, an unquantum effect. A small detector won't see that. It's better that's why I'm talking about the bigger detectors. If it's a smaller detector, it's less often that it'll get a chance to go through and do more scintillations within the detector in response to one source. So that's about the setting of the doc over here framing. That's about how to deal with the lower level and upper level of the discriminators, the single channel analyzers. And so I have it preset here. And so this is the gamma ray pulse height spectrum. And so we get to see the pulses that are all well behaved. And these are the pulses that are showing up in real time. And I'll put it on persist, and they'll start to superimpose, and you can see that they're well behaved. It's possible that some pulses will overlap, and then you get misshapen pulses. And that's if your source is too strong. That can happen. But you can see that does not happen. That is not the case. So there are things to watch out for with different strange sources and detectors, how they respond. So you look at you get to see the shapes of the pulse. And so I'm going to turn back on the timing histogram. And that is responding to the square waves that are coming out of the SCA. And I could show you them. Let me get some stuff out of the way. It should be visible here. There are these square waves that are used, that I'm triggering on to be able to see the coincidence histogram. So the way you read that, I developed how to do this, by the way, on the LaCroix. The LaCroix has all these features. They didn't say how to do it. I figured out how to set this up to see all this stuff, to see the pulse height histograms and the timing histograms. There's a smart trigger, and if I go to the regular trigger, it'll sort of destroy the experiment. But let me just stay with the smart trigger as to what I have. It's edge trigger on channel 4, which is this timing which is the second one that it's the further back detector. Trigger on channel 4 after channel 3, which is this timing from the first detector, the timing pulse, within some range. And here I have it 2 microseconds. And so then these cursors, these vertical cursors are important, and you get to put them wherever you want. And so the numbers that show up are what is read, what happens in between these cursors. And that's for both the pulse heights to go to the pulse height histogram and for the timing difference histogram. So the numbers get read off over here. So you set it up so that you can read how many pulses happened in this amount of time, the duration of the experiment. So here we have this great big beautiful peak in the time difference histogram that nobody else sees unless they give it something that emits two, where they know there are two of their photons or whatever emitted at once. But it's only one at a time emitted. We know that from the true coincidence test. Let me expand this on trace C. And so you fill it, so you count how many are within the cursors here, the dotted lines, and it'll say some number in that time. And that's the rate of the experiment. And it's read, this time range is used in the chance calculation. And so here it's 50 nanoseconds per division, and it's 2 divisions. So we're reading how many coincidences happen in the window of 100 nanoseconds. In this case, you set it up however you want. So it's a 100 nanosecond time window. And so I'm going to go back to the pen board. I'm going to say let me first go up here. These counters up above, these counters are the singles rates that are coming in from the detector, that's coming out of the SCA, that are used in the chance calculation. So you get the number per time. There's a time clock here, and you get a rate. That's how I do it. So the number per the length of time of the experiment. So you get the rate for detector 1, you get the rate for detector 2, and then you use that time window, the 100 nanoseconds, and that is the equation for the rate of chance. Put in the numbers, you get some chance rate. Then you compare it to the actual experimental rate. So I like just putting it up here. So the rate of the experiment is this number per time. You get some rate, and you calculate it. Now, quantum mechanics will say it should just be 1, and other people have done it the same way, and they see it's just 1, and they're happy. That's what quantum mechanics would predict. But I see for this setup, when I did the numbers, it was 10, about 10. Now, everything you do will change this rate, and there are reasons. The detector, the size of the detector, the distances make a change in the rate. And I can explain those reasons, but let me just rattle off the list of variables, that some of the variables that I've done, and it lets you do spectroscopy. I call it photon violation spectroscopy, where you'll change the material of the beam splitter, you'll do the angle of the beam splitter, you'll do the chemical state of the source, you'll have a magnetic field on the beam splitter, you could change the temperature of the beam. All of those variables are readable by the rate that you go above chance, this on quantum effect. It's a spectroscopy, and it's useful in material science. And so I've published this in a patent application in as far back as 2005, all of those variables and how to make it useful. But of course, the patent office threw it out just from reading the title pretty much. Photon violation spectroscopy. So, and then I did the same thing with splitting the atom, splitting the alpha ray. So there may be other things to get back to here, but I'd like to let me turn back on the analog persist. So that's very quickly how the experiment is done with gamma rays. Um, so yeah, I want to go to the alpha ray. That's what I'm working with. Just take a peek down here below to the chamber, because I'm currently working with an advanced version of my alpha ray splitter where the angles of the detectors matter. And so that I stopped this experiment in order to turn this other gamma ray experiment on to do this demonstration. But what I'd like to do now is I want to go over to just show something about the alpha rays where it's possible to do the experiment with without a vacuum chamber if you make everything small. But first, let me just show I have an alpha detector and the polarity is opposite. So in this case, it's going negative. Let me start it over. Anyway, there are the pulses, and this is the pulse height histogram. So I'm going to clear sweeps. I'm going to see that happen. So when it's close, the spectrum pushes over to the left. Bigger in this case is to the left because the pulse is upside down. And so we're able to get pulse height spectra readily from detectors, and it needs an amplifier right on the detector for these small pulses. And there are different brands that they're not cheap, these detectors. Here's what's interesting. You pull it away about an inch. I'm going to start it over. And so it cannot go through about an inch of air. I'm going to push it closer and you'll start, there it goes. So the alpha ray is, and it's a smaller pulses. And you can see on both displays. You push it closer. So that's the way alpha rays work. If the experiment is small, then you do not need a vacuum chamber. It's possible to do the experiment with what are called PIN diodes. I forgot what PIN stands for. You take off the glass in front of the diode and they can detect alpha rays, but it needs to be in the dark. So you have to put it in an enclosure, and also you want it to be metal so electromagnetic interference doesn't get in the way. But and then but you have to make an amplifier. This is the CERN DIY particle detector that shows the schematic for the amplifier and the how to deal with it, and to do this on the cheap to do a detectors for alpha rays. But and it's possible, but I've not done it yet. I've not done the coincidence experiment with these small detectors with the PIN diodes. I've done it with conventional alpha detectors, plenty, and that works. It does the quantum effect. But what I'm saying is that it's possible to make in the future for someone to use the pin diode. Here's a bigger pin diode that is from Hamamatsu photodiode. And so the way it's done with splitting the alpha is that most of my experiments were done where it splits off of a gold leaf, two layers of perfectly pure 24-karat gold leaf is what I've had the best success with. And I've tried all kinds of beam splitters, different elements and thicknesses and whatever. But what's also pretty interesting is that the surface of the detector will split the alpha. So I've seen that for sure. So an alpha ray, the helium nuclear wave function, the atom can split like a wave. The splitting like a wave has been understood since 1930 by the work of Esterman and Stern, and there have been other people who've shown the wave properties of atoms. So what does it mean to do the wave properties of atoms? Well, Eric says if it acts like a wave, it is a wave, and you can give up the probability interpretation from my experiments. My experiments show that if you get 2 for 1, it's not a probability wave. You're splitting the matter wave. So that's the distinction. Anyway, alphas can reflect off of the surface at the same time as going into the detector. If it reflects, it goes to another detector. And that's what I have set up in this other chamber to explore different kinds of reflections and the angle to return to this. I saw this effect with the alpha rays back to around 2005 and published it 2007 in a patent application, which was immediately rejected, of course. But I published it in a few other places. Anyway, it's possible to do this on the cheap, and I tried building some amplifiers for it, and I didn't finish. So I'm trying to say that it's possible to do this experiment in many different ways. Let me go to one other way that I think is interesting to do for this experiment. And I have this on my lecture slides, a good diagram as to how to do it. So tell me if this looks clear. Does that look good?
Yeah.
Good. I have bismuth germanate scintillators will respond to annihilation radiation gamma, half an MeV of detector energy. And so it goes through the first detector to the second detector in coincidence. And so the scintillators is on photomultiplier tubes, the same as before. So it's a higher frequency gamma ray. So you have to use this other scintillator that emphasizes the photoelectric effect for that gamma ray and that kind of scintillator, right? So that's how you pull this off. And I did it successfully. Now, what's interesting about doing it with annihilation radiation, with sodium-22 as the source, so it's easy to buy that. You buy these sources from Atlantic Nuclear for a few $100s. And the beauty of doing it with sodium-22 is that there is a hot gamma emitted, a higher frequency gamma ray emitted in coincidence. It's an anti-electron that's getting emitted plus this other hot gamma. You can use the hot gamma as a trigger, and you do a triple coincidence, and you use a triple coincidence chance equation. I've done that successfully. Let's see. Right. An anti-electron gets emitted. It finds a normal electron. It annihilates, and it makes opposite going gamma rays at half an MeV each. You can catch one of them in the pair I just showed you. The other one can go anywhere. It'll go into the trigger detector, but the trigger detector is set so that it reads the bigger pulse, and you do that in triple coincidence with the other two, and you get to see a very convincing unquantum effect with a radioisotope that's been very well studied and annihilation radiation and so on. So I did that as well. I did many experiments. Just wanted to mention that setup. So I'm pretty much running through quickly the kind of tests I do in the lab, and I'm opening up to any kind of question.
Thank you, Eric. That was very detailed. I will have to look at it again
Right.
to understand everything. There was several questions by one person. I shared to him the Zoom link, but we can I can show now the question here. I put them here.
Let me set that
I don't know if you know this person. So let me put, can you see? So the first question is, are you recreating something like Klaus or Friedman 1972? Or is this not about polarization entanglement?
All right. All right. Let me explain that. Where's my red pen? I want to sit down and do this. The Friedman-Clauser experiment was about what I call a two-detector experiment. And it turns out that Clauser also did the one-detector experiment. So the two-detector experiment is there's something in the middle and it goes coincidence, and then they look at the angle relationship between the two sides, and they compare to Bell's theorem. That's the two particle experiment. What I do is the one particle experiment. So there's one that comes out, and then you beam split to two detectors. So this is the two particle experiment and the one particle experiment. So the understanding of the two particle experiment came from those same researchers who did the one particle experiment. And when they saw it, they saw that noise in the histogram, which was about confirming quantum mechanics. And then they say, well, it's non-local. The non-locality happens in the one particle experiment because it went, they think, one way or the other. Can you see what I did? Okay. But I showed no, that it doesn't do that. That this idea of quantum mechanics and non-locality in the one detector experiment fails. Because if it goes one way to make a click here, it eliminates that it goes the other way, because the wave function by the model of quantum mechanics goes both ways, and that's entanglement. If the wave function goes both ways and then it shows up one way, it's that it eliminates the other way by entanglement. So it's the one particle entanglement idea that came from doing this experiment poorly, and then they apply it to this experiment and they think about that quantum mechanics is non-local from this experiment. They have it on in their idea that it's non-local. Then they go to the two particle experiment, and they say, so I have to draw, well, what is the result of the two particle experiment? It's confusing because they actually did the two particle experiment pretty well. And so they compare to Bell's theorem, where the angle, I have to explain all this, the angle between the polarization on the two detectors is here. And the coincidence rate is here. So Bell's theorem predicts a straight line. And you know that because all the terms in the inequality are just simple algebra, no sines or cosines or anything. But the experiment that everyone is all hyped up about and they gave the Nobel Prize for, the experimental gives like a sine curve. And so they say it's different from Bell's theorem, mostly here, and that's where they do the experiment. And then they say, well, Bell's theorem has to be right because we did just down to earth kinds of assumptions behind it. But you look at the curve and say, oh, it's different. And they say, oh, quantum mechanics fits the experiment. So the experiment and quantum mechanics agree. And it also is similar to what Malice law would come up with. But it disagrees with Bell's theorem. So to get through all this, to understand what's going on, Eric says Bell's theorem did not understand what I call the preloaded state that I'm revealing by getting 2 for 1 in the experiment. Bell's theorem left, so that's where the hidden variable is. So maybe I need to explain the loading theory again to see that there's such a thing. I mean, how to picture this preloaded state. So, but that's the different. That's what all that entanglement stuff is about. That's why they think that way, because they're thinking about the way this works in terms of probability. And it's confusing because the experiment is done right. This experiment will not see, the two particle experiment will not see the distinction between the threshold model and quantum mechanics. That's why it's confusing. So they do the experiment and they say, oh, it's different from Bell's theorem. Bell's theorem did not include the idea of a preloaded state, and I expect that if they redo the theory, whatever they're comparing to, they'll get a curve. So what is this loading theory I'm talking about? Sometimes I even have to do a skit with cups to explain it because not everybody knows what I'm talking about. And I'm going to just take a minute to do it. It's like I'm saying everything is like there's such a thing as a full cup and an empty cup. And we're going to take this full cup's worth. We're going to throw it over here. We don't know what the state is of the other 2 cups. These are the 2 detectors. This is the source. So I'm going to do this. Boom. It's full. And now all of it spills over. So I'm saying all of nature works this way, that it's a rule. When it gets full, that's when it spills over. And you do not see what the preloaded state is unless you do my experiment to see through the illusion that there's such a thing as a preloaded state, because I get 2 for 1. Now, it's not as if I'm getting energy from nothing. We embrace energy conservation, but we're comparing the idea of energy conservation as seen in terms of particles and as seen where it allows for such a thing as a preloaded state. So my work is a very fundamental challenge to quantization itself. And so I think I've answered the question about what Clauser Friedman did and Aspect. It turns out that the French team, Alain Aspect, did the same 2 equations. Aspect did both the 1 particle test and the 2 particle test. They were both familiar with those setups. And they did them a little bit differently, but they both handled those general ideas.
Rick, what do you think about this comment? If you do the same with Alain Aspect 1982, his raw data can also be predicted by a classical local model.
You don't want to do it the same way as Aspect did. He did it with visible light, and there's no pulse height resolution. And there are a list of problems with saying whether you have a emission that's one at a time to deal with when you get to reading coincidences. So I have good exposure of those experiments in the history of physics, both by Clauser and the Aspect team, and what they did and their mistakes. So it's almost not fair to me. It's all in my previous lecture slides.
I see. There was one comment says that they never published raw data. They published post-edited data. The IBM computer was the only thing that saw the raw data, the raw coincidence counts.
I can't understand what you're saying.
Um, Let me show you.
I can't see anything.
You can see this one.
Not, well, wait.
I can copy it and make it bigger.
All right, what's
Can you
going
see?
on?
This one. Can you see this one?
They never published raw data, though. They're published post-emitted data. The IBM computer was the only thing they saw. Look, I I don't know who you're talking about
Mhm.
and what IBM computer. Look at the paper. I publish in my slides the important parts of the papers where they claim that it's photons. The paper by Clauser, 1972, and the more famous paper by the French team, uh,
In 82.
Roger Granger Aspect. And there were problems in what they did. They didn't use the right triple coincidence chance equation. They made up another equation. There were a bunch of assumptions in what they say is one at a time. So I get the opposite result they have. So I see these things all the time thrown at me. What if this and what if that? And my response is, it's time for somebody else to be doing my experiment. So I'll go to the next question.
There was many, but just focus on maybe the last ones here. So this one was this. Thank you very much. I appreciate sharing this, and there is more to learn about this topic.
That's nice. That's
And
very good. That's what I want to hear. I
and
like nice pats like that.
yeah, it says the main reason I think that in particular is that this is what the raw aspect data shows, and the Clauser-Friedman data never contain raw weights at all.
Well, uh, Clauser-Friedman, like I said, that's about the two particle experiment. It's a different experiment. So uh, I, I, I don't remember just how the data was, but that's a different thing altogether.
Yeah, but then he said in the end, I need to review your explanation in detail to understand it properly. Maybe it is related to what I have looked at, or a different explanation.
The explanation is best understood what I did with the cups to understand that there's such a thing as a threshold, some state sub-quantized that you won't see unless you know how to see through it by doing this two-for-one effect. So that's the thing to start with to understand. There's more to it about how this can be that I've covered in my previous lectures. And it's related to the atom splitter and the electron wave properties. How can it be that what we think are particles can act like a wave? Well, that's a very important part of my theory that I claim to have conquered that. And if you don't understand what I call this principle of conserved ratios, you're going to wonder how this is possible that waves can act like particles. I'm saying that there are properties of the wave that show, depending on the experiment, that it acts like a wave, that it shows its particle property as clicks in the detector, where a particle does not have to go across space to make the click in the detector. There's a threshold that can make the click in the detector, but there's more to it. How does the wave go across space and transmit that it's an electron wave or a helium wave or a whatnot? And that was really the important part of my theory. And it's in my previous work. So it's that if you look at the experiments that are famous for the wave properties, you'll have like the de Broglie equation, which will have a the de Broglie equation will have like an H to M ratio, and there'll be another equation that'll have a charge to mass ratio. The equations that are famous for the experiments that show wave properties have ratios of our famous constants. And the other ratio is the H to E ratio. Okay. The trick, I, I sometimes call it the ratio trick. This is really how I figured it out first in year 2000. And once I had this idea of understanding the ratios and a few other properties of the waves, then I was able to, with confidence, go through and devote my life to do all these experiments. What it's about is that the experiment does not, like let's say electron diffraction. The experiment where it would use the de Broglie equation. The experiment does not read the M or V's or any of these individual. The experiment reads the velocity and the wavelength. It doesn't read the H or the M as quantized. It reads the H to M ratio. The experiments that display wave properties will tell you the ratio. And that means you do not need to have a whole H worth of action, a whole M's worth of mass. You can have less, and the ratio is conserved. So my theory of wave particle duality is that the constants are thresholds and the ratios are quantized. Then you get to see through everything. You get to understand these matter diffraction experiments. And then there are some experiments like how do you diffract buckyballs and stuff like that. And I have a way to explain that away. So there's 100 years of experiments where people are going to throw it at me and say, "Oh, how do you do that?" You start here. You start here with understanding the ratio. So if there's, I was afraid of this, that I'd have to do all this. Let's say you have an electron that's a charge wave that goes out, and you put it through whatever kind of double slits, whatever you want, and it'll show up with an interference pattern. How do you do that with particles? Well, you don't. It's a wave. What you have to do is address how is it that the dots show up to make it look like a particle hit there. That's the real difficulty of the problem. The answer is it's a wave. There are properties of the wave, and it loads up just like what I did with the cups, and it shows itself. And if you were to take any piece of that wave, any cubic volume of it, and picture, well, what would be the mass of that? See, it's these little m's that kind of trick you. Oh, it's the mass of the particle. It's not. It's the ratio of the charge to mass, any of those ratios that are there in the wave, that any piece of the wave would have the conserved ratios. And that's the conceptually difficult part of my theory, to understand how this could be that this guy is saying that it's not particles going across space and that it's not a probability wave. This is it. This is the answer. This is what I did first in year 2000, to understand some kind of theory about how the wave can transmit its identity and show up. This idea of a loading of like Planck's constant, and it's in my lectures. I spend time on this. I show Planck's second theory. Planck's first theory was that there's what everybody is taking up now: quantized absorption, quantized emission, time, energy. And his second theory of 1911 was continuous absorption and quantized emission. That's the loading theory. Planck had it right. So you do not need to have quantized action to explain the black body equation. And that's the situation in many cases, where there are different equations that will fit the experiment. And then you go back and say, well, how did that equation get derived? There are different ways to derive the equation. And that's what Hallam and I were looking at. Well, how do you derive the Compton effect? There are different models that come up with the same equation. And so I did a derivation of the photoelectric effect and a few others to sort this out. So the thing that happened that tripped people up in the history of physics was they may have understood about this continuous idea of loading that Planck introduced in 1911. But this was not quite right. Millikan examined the idea in the photoelectric effect, and he got it right, that there could be a dormant part where it's not quite reaching the threshold, and then it only needs a little bit to set it off to emit. And so that's what's going on, that the absorption is an arbitrary curve, and then it can emit suddenly. So what's happened in our textbooks is they convince everyone away from this idea, because they don't use this. They use this, and they count, well, how much time would it take to load up? And they'll have you do this as a homework problem. And then you'll get something like a minute or some crazy number. And then they'll compare to an experiment, and they'll quote Lawrence and Beam's The Element of Time in the Photoelectric Effect, and they say, oh, well, it responds in like a nanosecond or a few nanoseconds. And they say, well, it cannot be a loading.
Mhm.
So they're comparing to a unworkable loading theory. If you revise the loading theory so that it could be arbitrary absorption, and then a little can set it off, then it can work. And there are many papers I see, like it's in Max Born's book, where he says it cannot be a loading theory. Well, I'm sorry, you just didn't understand what a workable alternative to the loading theory might be. Now, Millikan had it right is around 1930 something in two of his books, and I give pictures of it in my lecture, how he talks about it.
Did he abandon his idea,
Yes,
basically?
yeah. Millikan did not understand how it could work, and what it looks like is that he did not understand, like, my principle of conserved ratios that lets it work. So he gave it up. Nobody else talked about a load. And I was looking really hard and low, and I have a library full of books that that I've been collecting and seeing, and there's my library
Mhm.
of books, and my assistant showed up, the
Yeah.
camera person,
Uh,
to see who
what do you
was
think,
looking
Eric?
for this.
Yeah, sorry, what do you think about the water wheel I showed? The water wheel
Uh,
analogy.
yeah.
Right. If
Um,
I try to find something to show visually or to have some idea to see
all
how
right.
this can work.
Yeah. That the visual ideas that I like using. Uh, there's a musical string analog where it loads up and then it changes harmonics. That's a loading theory. There's there's a commercial where they have this great singer uh, testing the tape recorder, and there's a wine glass, and it gets ring, and then it breaks. So that's a loading theory, and then it shows up suddenly. So there are other analogs that are closer to it, where it loads up and it shows itself. And so this business about it being a rain of particles does not pass the true coincidence test. So it's not that. So we eliminate that idea with this tried and true test to know that the source is only one at a time, not a rain and not an intensity of the waves that show up at the detector either. It'll happen with a wide range of rates. It's even better to have a slower count rate. And but I forgot to say, you have to subtract background in these tests. So it's really a sequence of like three tests to do what I have. The recipe
Eric,
is
yeah, sorry, Eric, I have a question about alpha gamma rays and alpha particles. How is it dangerous for someone to try to replicate the experiments? What the
right,
rules or
right,
what he
right.
has to?
I,
Yeah.
I worked with a friend of mine who was the health physicist at Stanford Linear Accelerator, and he he from all that experience, as long as you do not touch the americium or eat it or wear it, it's fine. You
Okay.
just take simple precautions and it's safe.
Okay. I want to show some comments in the. Can you see my screen?
Yes.
Okay. So people from India. You have some people from India, and then so the way I think about the dynamics behind these experiments is mostly classical wave theories with detector outcome based on some similar effect derivable from the wave mechanics. So I think it's close to is
Yeah,
similar to what you.
that's right.
I don't really.
Schrodinger's original idea was that the electron was a smeared out kind of wave, a matter wave. And it was born very soon after that changed the identity of his psi wave function to a probability amplitude. So it is very similar to the early wave mechanics of Schrodinger and de Broglie. The thing about those waves, so I handled that early kind of wave mechanics in the understanding of what is the wavelength of in the de Broglie equation. And I did that by a simple algebraic connection between the de Broglie equation and the photoelectric equation. And you do that by understanding that the charge interaction between light and charge is about beats. So there's a slide where I show that Schrodinger, in his first famous paper, uh, says that light is about interacting with the beats. And you know that from the structure of the hydrogen spectrum, which has two terms, the difference between them. So you just write out, well, the frequency of the light is equal to some constant with a bunch of terms. And then there's, I'm going to write it a little different, the frequency of the psi wave by another frequency of psi 1 and the frequency of psi 2. So you simplify the hydrogen spectrum equation to this, and you realize right away it's about difference frequencies. And Schrodinger saw that and wrote about it. And that difference frequencies are about beats, and that light is about interacting with the beats. Now, in my lecture slide, when I do this, but I'll have it right here, Schrodinger did not realize that light would fit with 2 beats. So it's this factor of 2 that the frequency in converting the de Broglie equation from it's about saying that the wavelength is actually the wavelength of a beat, and the frequency that they happen is about beats. So if you do that, and it's the velocity of the beat and the mass of the beat, you do that, but you convert it to light. I'm sorry. De Broglie had it where the wavelength was, the mass wavelength was sort of undefined. It was the probability wave. Who knows what it was? That was the big question. What is a wavelength of? They have it as the velocity of the particle and the mass of the particle. So you correct de Broglie's equation by understanding the model that's apparent that Schrodinger pointed out of the interaction between light and charge to get the factor of 2 correction. And it's very simply that it's the frequency of the light is twice the frequency of the beats. I think you put a 2 here. 2 times the frequency of the light. So there's 2 beats. So you do that. It's a very simple derivation, but it's inspired by the model. You use velocity equals frequency times wavelength, and you put these together, and you get the photoelectric effect equation. And so that's pretty interesting. I've connected a wavelength equation to a frequency equation. Now, nobody did that except me. So that's the way to correct the early wave mechanics to have it make sense so that they don't just throw it away and turn it all into probability waves. That's the first step. And then when you get to the photoelectric equation or just the de Broglie equation, I'll just stick with the de Broglie. Then you just put the mass on the other side and understand the ratio trick. That fixes the mess. That fixes the whole thing. So that's my theory.
Yeah, so Eric, for all experiments that have been done, it is always, there is always a ratio.
Yeah, the ones that I found
Like
where they express the waves,
yeah.
there's a ratio between the constants.
So, for example, so the Millikan experiments also has ratio? Or?
No,
No.
no. That's not a wave diffraction
Not a wave.
experiment.
Yes.
And so that's what confused people. So you do the Millikan experiment, and you're balancing a droplet with some horrendous number of charges in it, and you get the right charge constant. But it's a very different physical situation that I'm identifying from when you do it with waves and do diffraction experiments. So what I'm saying is going on is that the surface charges and the ensemble of all the nuclear charges, it expresses the threshold aspect of charge in this state of matter of a macroscopic drop. That's a different expression where when you smear it out in an electron gun, then it's just the wave properties that are expressed. It doesn't express the particle aspect of the threshold model. The threshold model has both. If you're at the threshold, it looks like particles, but there's a sub-threshold amount that you can see in the experiments that I've developed. And so,
But why we cannot see them in the Millikan experiment?
right, the Millikan experiment does not see fractional charge. It sees the whole charge. But uh, bear with me, I tried to address this very issue by how to see. There's an experiment that I devised for how to see fractional charge, and I spent a few years on it. And I have pictures in my slides. And there's a way I built a mass spectrometer for alpha rays to in a magnetic field that will show the charge as a function of angle here. And what I did is I tried to make an electron gun to influence the alpha, to change its charge. And I was able to see the three charge states that happened here. And there'd be like uh, no electrons, one electron, and two electrons versus the angle. So I made a mass spectrometer that could see this, but I never had it working. But this can be done. I had trouble making the electron gun. Uh, it has to be a low velocity to do a velocity resonance. So some future person will be able to look at what I did and say, oh, let's fix this and see that the idea was that to change the charge so that this bottom here would come up and that would indicate fractional charge. So there's a way to show experimentally the distinction. It was a very hard experiment. I was not able to make that work. I know how to make it work. But still, just understanding that the state of matter is so different, it makes sense that it would express the particle, the charge constant with an oil drop and not express fractional charge that way. There are all these surface charges. There's a nuclear realm that affects it as well. So yeah, that's my answer to it. It's about the experiment, about how it expresses either the threshold or the wave property. The threshold model is able to do both once you understand it, depending on how it fits the experiment.
Yes, I see. Eric, let me share some other comments. Can you see my screen?
Yes.
So the first one, it says, I don't really buy the particle idea at all either. So it agrees with you.
That's nice. Thank you.
And sounds cool. We'll definitely review that work. So
Thank you.
positive. And you just need quantized transfer of energy over momentum between light and matter system, in addition to the linear Maxwell-like forces. Yes, agree.
No.
No?
No. Quantized transfer of energy momentum between light and matter system. No. No. No, I'm showing that quantization, the model of quantization fails because I'm starting with one and I'm getting two. I'm showing it's not quantized. It's a very fundamental thing I'm doing. People usually don't know what I'm talking about.
But
I'm
I mean,
saying,
but when it says between light and matter system, so it means
yeah,
the same thing, like at the
yeah.
detection, not at the characteristic of the light. So I think it's similar to what you say,
Well,
but maybe
the light, if you go around diffracting light and you try to do it with particles, you're going to be lost in wave particle duality and the probability interpretation and collapse of the wave function and all that mess. So it's about not quantizing light
yes,
to
yes.
show, all right.
It's and then also the photoelectric effect has proof of particle is just real strange to me. Same with Compton scattering. So I think it's
No, no, that's
yeah,
both wrong. You can
yeah.
use the particle model on both of those derivations and experiments, but you can use a wave model. And so you
Yeah,
can look at my wave derivations and models to come up with the same equation.
yeah, I think this is what he said too.
Oh,
And
yeah.
he said even just how a small raindrop has series of reflection of a pulse of light leads to linear recoil and a scattering angle like Compton with some differences. Uh, and
I
then
don't
it
know.
says, I have no idea why electron models will not do the same with what is just like a classical light wave for Compton in particular.
Well, it depends if you're using a particle electron or not. You know, as soon as you say the word electron, it sounds like a particle.
Mhm.
So it's very easy to be confused. Once you just talk about charge when you're doing a diffraction experiment, if it holds together as a particle, it's not going to show diffraction. Uh, so it's a simple idea. Particles just do not diffract. Let's try to figure out what's a particle. I mean, people have been arguing and confused over that for 100 years. They'll say, "Oh, it has a wave property." A particle. The easy way to do it is to say a particle will hold itself together and a wave will not. That's the distinction between a particle and a wave. A wave spreads. And once it spreads, it's not going to be able to recollapse itself altogether again. It's spread. So you need to deal with that to avoid the measurement problem. And the way you understand that is starting with Planck's second theory and then correcting it with the ratio model.
Sorry,
Particles don't diffract.
let me show again. I think it they agree with you. I just let me show again another comment. It's not here. Okay, someone asked if this will be saved to others later. Yes, it will be available on the YouTube, and also Eric's is recording, I think. Yes.
Yes,
Yeah, and says so Jürgen said in emission only. So I forgot to say that I don't mean quantization in absolute terms, just means that the emissions are quantized
that's
in a
right.
sense, not
That's
that the,
right.
yeah.
That's right. It's quantized emission, and thereafter the wave can spread classically. And then with the loading idea, then you get to a threshold, and it has a sense of quantization in that there's a threshold. So that's the way you make sense out of it, and have waves go across space to address the diffraction phenomena. Because it's straight from that first sentence of the model where I showed you the model of the photon, that if you reconverge the beam, it has to go both ways to generate an interference pattern. It's a direct contradiction to the first half of the photon model, which is that it goes one way. They realized that it was a contradiction from the earliest times. That, and in that sense, that's why no one understands quantum mechanics. It's because quantum mechanics requires that you give up understanding and you just take these two contradictory parts of the model and say, well, that's the way it is. But it's like saying God is crazy. But no,
Yeah,
nature is not crazy.
yeah, I have a point of view about this. I think in
That's
any
right. That's
in
the,
any in anything in physics, we should be able to have analogy that makes sense. If we don't have, I think then anything is possible. You can invent any idea, strange idea, and say this is how the way it is doing. And I think if we don't have a clear picture, it's better to say I don't know what's happening.
that's right. That's right. So what's happened from all of this entanglement and superposition is that people have made up all these acts of desperation, like many worlds and times going
Yes.
backwards. I mean, people with degrees are coming up with these quantum weirdness ideas, No, you don't need to go to such desperation.
Yeah. So Eric, actually Jürgen says that he was agree actually with you. That's what I said. It was not a criticism of you, just
Thank you.
an oversimplified analogy.
Thank
My
you.
point was simply classical wave theory can produce the same type of effect pretty easily. Uh, I
Good.
don't, I don't understand why people bought the particle picture at all.
Right. Right. Well, please, I have a history set of lecture slides that will show how they misinterpreted experiments, how it happened. Uh, there are My best writing is the lecture slides, which is at the very top of the website. I have a file on the history, a file on the theory, and a file on the alpha ray test, and another file on the gamma ray test. That's the place, please, to read. And so you're talking about the history. I've addressed these issues. What happened? How
Mhm.
did they go astray? It's about interpreting certain experiments. So that's just like required reading.
Okay, okay. So I think for today we have seen all the details about the beam split experiment. Maybe later we will. So today it was you talk about the gamma rays and alpha particles, or it was only I forgot it was only one of them or both
Mostly the gamma ray
gamma
was
rays.
running. And then
And
I just showed a simple spectrum and some detectors for the alpha ray. But the alpha ray experiment works the same way, the
okay,
same electronics, the same NIM
okay,
modules, and the same LaCroix setup.
okay,
The detectors are changed.
okay. And so, do you want to have another session to talk about um, other things in more details? For example,
Yes, yes, I'd love it. Thank you, sir.
the double slit experiment, maybe.
Okay.
Mhm.
I have a slide for that, but I'm getting worn out.
Okay, okay. Yeah, we can do that for our next meeting.
Thank you, sir.
Thank you very
This
much.
is great.
Thank you. Thank you very much. That was very excellent presentation. Excellent talk, Yavin. Thank you.
Thank you. Bye bye.
Bye bye.